What up, chemistry students? This is Mr. C coming at you with another video. All right, it's gonna be very short and sweet. We already went over heating curves in class, but I'd like to revisit them for a couple minutes. Okay, this does not take over from the other day's lesson on the heating curves. It's just a quick revisit of what some of the parts mean and how that not all heating curves are of water. Some people think that water's, heating curve is very easy and simple to understand, but you can do it with pretty much any substance ever. All right. So for instance, I'm going to look at the heating curve of iron. All right. I've got a big old cube of iron. Iron melts at 1500 degrees Celsius. All right. You can't melt iron by putting it in your oven and saying, all right, turn the oven high, it's going to melt. Nope. Okay. Not going to happen because your oven does not get to 1500 degrees Celsius. If it did, a bunch of stuff in your oven would melt. So iron, pure iron, melts at 1500 Celsius. So right now, this iron is, I'm going to say on my graph, it's like down there. Okay. It's around 25 degrees Celsius. So in order for me to melt iron, what I need to do is get this iron to get to around 1500 Celsius. So on my heating curve, all I got to do is heat it up. How? I don't know, get some way to melt iron. Heat it up until it gets to 1500 Celsius. At this point, all those little intermolecular forces between the iron atoms, the ones that are connecting the iron atoms to themselves to make it the stable structure it is, they start to break. So when we took notes on this, that's what's going on here on the heating curve. Note that as iron melts, the temperature stays constant. That's what this big line is. See, the temperature doesn't change. So a very common misconception is that as a substance melts, its temperature goes up. Nope. As a substance melts, its temperature remains constant. Okay? The graph makes it obvious. Well, it doesn't go up. There you go. There you go. Because what's happening as you are heating up the iron, look at the x-axis, energy input. The more energy you're putting into iron at this time, it's breaking those intermolecular forces. And again, from your vocab, thermo and phases vocab, what does that actually mean? Well, inter means between. Interception in football, it's when a defender gets in between the quarterback and the receiver and catches the ball on defense. Interstate, that's a road or an expressway that goes between states. Intermolecular forces. Inter means between. Molecular, you can think as small particles in a substance, atoms, molecules, whatever you want. Forces are little strengths. Okay, it's how strong something is. Little pushes, little shoves. So in a way, you're breaking the bonds or the connections between particles. So once iron gets to this point, what we're seeing here is that the melting is done. Melting time is over. All right. So all the iron from this cube is now a puddle of iron, a puddle of liquid iron. Okay. And what happens then if you keep heating it up? It starts to actually change in temperature because the iron is now an entire one state of matter. It's now a liquid at part 3. Okay? So in the video the other day, when you watched that, I think the most popular part may have been like this part, like part 2 here, and this third line. All right, that's what you see most often as a human. You don't see one as often. You really don't see that 5th one as often up there. That's fine. So at this point, the iron starts changing temperature. It's also heating. It's heating up this whole time. And when it gets here, that's when it starts to boil. So if you can imagine boiling liquid iron, it's hard to, I mean, it's easy to think about, hard to see in real life. But what's happening here then is as you heat it up, note again, the temperature remains constant. That's your flat line. So iron, as it's boiling, is staying the same temperature because that extra input of energy is used to break those intermolecular forces. Because when iron's a liquid, check out this picture down here, there's still some intermolecular forces. They're still connected in a way. They're attracted to each other. But to form a gas in which all the particles are super far apart and not really attracted, you got to give it a ton of energy. And that energy is used to break those attractions. And then once it all boils, now you have gaseous iron, which is really hard to think about. And as you heat that up, the temperature increases. So that's really it for heating curves. Some people think you can't go backwards. You can go backwards, it's fine. I like to relate it to an interstate. I-90 does not only go to Chicago, that's absurd. It depends on the direction you're traveling. You can go to Rockford, just go on I-90 west. You can go to Chicago, go to I-90 east from here. So it depends on your direction. If you remove energy and you go this way on your graph, you are removing energy, and therefore you are not boiling anymore, you are condensing. All right? You are making gaseous iron turn into a liquid. But now you're cooling down the liquid iron, and you are freezing the iron until it all freezes, and then you're cooling it down. Okay? Freezing is not just for water. A huge misconception is that when you freeze something, it's cold. No. Have you ever felt 1400 degree iron? It ain't cold, but it's frozen. Okay? Frozen is not just a movie and it's not just ice. Okay? Please get that out of your heads. This iron block is frozen. I'm fine. If I heat it up to 15 or 1000 degrees Celsius, the iron block is still frozen, but it melts through my hand. Okay? So please, that is a misconception that I want to get over with. Frozen things are not always cold to humans. All right? Fun. Cool. Let me know if you got questions on things. Hope this kind of helped just help out with the what a heating curve is, the fact that you can go both ways, just like an interstate, just like a drive, or just like an expressway. Bye.